Good evening, everyone, and thank you for joining us tonight. Thank you, Rich, for the introduction. We are asked to provide more background on ourselves, and it's my childhood photo generated by AI because I couldn't find my childhood photo. I lost my hard drive some years ago, so I guess it's pretty much similar to the reality. I born and raised in Iran, a country in West Asia, in a small city in that green stripe near Caspian Sea named Lahijan. It's famous for many farming activities, including tea gardens, and there are many surrounding villages near Lahijan. For example, Tustan, where my grandparents lived, and near those beautiful paddy rice fields. But as a kid, my favorite farming activity was silkworm farming that can be used to produce silk and knitting these beautiful Persian carpets. When I was 18, I moved to Tehran, the capital city in Iran, to continue my education. I did my Bachelor of Science in Iran University of Science and Technology. And as Rich mentioned, I did my Master and PhD in Tarbiyat Modarres University in Tehran. Then I started my career in a relatively small university near Tehran, Qom University of Technology, where I was an assistant professor of electrical engineering, and I had many brilliant students working on pattern recognition and computer vision problems with different applications from medical imaging to cultural heritage analysis. For example, in this study that you can see, we classified Persian miniature paintings using machine learning and AI techniques. In another study, we did analysis on color pigments of ancient tiles that belongs to 700 years ago using hyperspectral imaging and also machine learning techniques. Then I moved to Italy to pursue my career at University of Genova near this beautiful historic port of Genova, Porto Antico, where I was an assistant professor of telecommunication, and I also involved in a project called Return about the climate change, where we did several interesting projects about environmental monitoring using aerial photography and also multi-spectral satellite time series. And finally, I found my way to Alaska at Geophysical Institute at Hyperspectral Imaging Laboratory, HiLab, where we are doing some exciting projects that I'm going to talk about those tonight. With that, I will hand over to Martin, my colleague. Thank you.
Yeah, first, thank you very much for the introduction, Rich. Thanks for coming, and thanks to everybody who is attending online. My name is Martin Stufer. Thanks to NaturalCell, he gave some good inputs how to start this talk. So I don't expose myself with AI. It's reality. I was about 9 years old, had no interests in climate sciences those days, more in sneaking out with my bike or staying up after bedtime. I'm coming from Innsbruck, Austria. It's somewhere out there in the West Europe. Innsbruck is known as a tourist city. We have it's a student university town, over 31,000 students these days. which means every quarter inhabitant is a student there. And it's also known for actual reasons. 50 years ago, Innsbruck hosted the Olympic Winter Games in 1976. Oh, that is in the center, in the heart of the Eastern Alps. I was lucky to grow up in this beautiful city and also do my graduate studies at the University of Innsbruck at the Institute of Meteorology and Geophysics. And it's completely messed up. I did my graduate studies in South America, in Patagonia, studying climate response and dynamics of Perito Moreno Glacier. Perito Moreno is in the southern Patagonian ice field, and it's a UNESCO World Heritage Site, beautiful area. And I spent over a year there within the years 95 to 2000. Over a year, my little tent next to the glacier, and did all kinds of research, built up weather stations. We had about 250 pounds of dynamite to do some seismics to measure the depth of the glacier. You can imagine in a protected national park how easy it is to get dynamite there and even to detonate it. People even don't get permits to go there, to walk there, and it was a wild, beautiful time. We didn't have any safety regulations those days, and so I even could measure the buoyancy of those floating ice pieces. We're just walking on them and did all kinds of fun things. In this talk, I could talk probably for hours about Patagonia, but coming back to the topic of today, I want to talk a little bit about global and Alaska climate trends, warming trends, what are some main climate drivers, some challenges, risks. And then I want to talk about, Rusby will take over and focus more on the AI stuff and on our HiLab. Starting with global temperatures. Those are global temperature anomalies from a mean 1950 to 1980. Monthly anomalies in this climate spiral. One cycle is 1 year, and you can see how temperatures change from long term, from 1880 to 2024. And how those changes appear. So really strong increase in temperatures in the last years. We had, in fact, the last 3 years, continuous record temperatures. If we compare it to the pre-industrial temperatures, we had 2023 to 2025, every year, temperatures above 1.5 degrees above normal. If you might remember the UN Global Climate Conference in 2015, when there was a goal decided and agreed on to have keep the temperatures below 2 degrees, preferably below 1.5 degrees. The last 3 years, we already exceeded the 1.5 degrees. 2024 was the warmest year on record, and a continuous above 1.5 degrees. So temperatures are rising rapidly. If I go to Alaska, here are some temperature trends, long-term climatological signals of temperatures for main cities across Alaska. You can see, maybe I go back to the laser pointer. Most pronounced, those are decadal trends. So if we have in winter in Utqiagvik a decadal trend of 1.29 degrees, then that means in 100 years, winters got 12.9, about 13 degrees warmer. Or 50 years ago, it was 6.5 degrees colder than it's nowadays. Mean winter temperature in Utkargik are now minus 10 degrees. So it was minus 16 about 50 years ago. Those are long-term changes. What's most evident, so more reddish, the stronger the changes. Most evident that changes are not homogeneous across the year. The most significant changes are in winter, spring, and especially in fall. And most of the changes, or the strongest signal, comes from the Arctic. Of course, that's related to Arctic amplification and sea ice. My colleague Bill, he's somewhere here. I asked him last week, Bill, make me a climate spiral for Alaska. And he did a great job. Here we go. That's similar to before, monthly temperature deviations, long-term deviations from a normal. And you can see most of the deviations in Alaska also in the spiral show up in the winter month and also from fall to spring. Least deviations, least variations of temperatures in the summer months. Looks pretty neat, right? So I'm talking about warming, and who was here in December and January? So you probably all thought the guy, what is he talking about? It was pretty cold, and I'm still cold to my bones. I'm not selling my bunny boots. It was, pretty cold. We have those graphics on our web page. We often get asked, is it warmer or colder than normal? Those graphics, we have them for many cities and locations around Alaska. We update them daily. And you can see the black line. Those are normal temperatures, what we would expect if everything would be according to climate. And the blue and red bars are the daily deviations from a normal. So if it's blue, we have it colder than normal. Red, it's warmer than normal. And December was significantly warmer. January, we had this one day where the temperature even dipped to minus 50. And I got, beginning of January or second week of January, a reporter called me up and said, hey, are we heading faster into an ice age than expected? And I was kind of flabbergasted. It was not the question you expect from a reporter, but I said, that has nothing to do with climate change, or little to do with climate change. That's weather, what we see there. We always will have variations in weather. Weather is short term, and climate is the average weather of over decades, at least 30 years. That's our agreement, and we still have weather extremes, and that was one of those extremes. The same precipitation, snowfall regionally is of course decreasing, but we know at the moment Anchorage has over 3 feet of snow, new record snow depth, over 300% than normal, so nothing is normal. But Juneau, we remember those pictures, still over 8 feet of snow in Eaglecrest right now, and 12 feet above Juneau in the mountains. So a lot of snow this year, a lot of interesting weather. So weather can vary all the time, and climate, we need to always distinguish between weather and climate. But it always gives a reason for people to argue about climate change and climate warming, but we see the signal. One of the main drivers for our climate is, of course, sea ice. And what we see here, that's, by the way, a picture from Point Barrow from last July. Some pieces of ice, and This graphic shows the seasonal change of sea ice. The long-term, the gray line is the long-term mean, and some variations around this mean. And the red dashed line, that was the absolute minimum sea ice, which we observed in 2012. You can see the sea ice normally increases over winter and has a maximum in March, decreases in spring and then in summer, a minimum in September. This red dashed line, that was a minimum below 4 million square kilometers sea ice. The sea ice typically changes by 10 million square kilometers. How much are those? Does anybody have an idea? It's hard to imagine. The whole US has an area of 9.8 square kilometers. So sea ice varies from winter to summer on the range of the size of the US, so pretty significantly. This darker line here, that's, by the way, the sea ice from last year, where we had a new low record of the maximum sea ice extent in March. And there's also, you can see a little bluish line. That's the current sea ice condition. It fares pretty along with last year. We might see a new maximum low record. The problem with sea ice, if sea ice melts, the surfaces get darker. We know water is exposed, and there's a lot more energy absorbed by the surface, and warming is accelerated, phenomenon which we well know of Arctic amplification. Warming is accelerated. If we look at the time series of the maximum sea ice, so sea ice decreased over the years. It's from 1978 to 2024, 2025. At the end, it decreased significantly. This maximum shows over 2 million square kilometers change. And if we put a trend line in there, how much are 2 million square kilometers or 2.3 million square kilometers we see here? It's about 1.3 times the size of Alaska. So that's what we lost in the last 45, 46 years. Quite significant. A main question with all those losses arises, and we are asked quite a bit, when will the Arctic be ice-free in the summers, in September months? There are a lot of studies out there, nature studies and high-ranked journals. And if you look at those are some ensembles of model runs for sea ice on the right. You don't need to look in detail, the top and bottom, but the models agree mostly that the Arctic will be ice-free about mid-century. There is, if we go even some less significant run, some runs even see an ice-free Arctic starting in next 10 years. But most models agree in the course of the second half of this century, with where we define, or scientists define, ice-free conditions if the ice extent is less than 1 million square kilometers. What does it mean, ice-free? Of course, increased Arctic amplification. We have a lot of more moisture in the atmosphere, and we can expect more extreme weather events. We can expect further rising temperatures and a lot of effects. If we go to sea surface temperatures, we see something interesting in the course of the last years. That's an example of Northern Pacific sea surface temperatures. Summer 2019 was our warmest year on record in Alaska. And sea surface temperatures were warmer than normal in the Gulf of Alaska and the Bering, significantly warmer. And then those temperature patterns can change in more recent years. Alaska temperatures were partly originally a little bit suppressed, not as warm as surroundings. And that was mainly due to those different patterns. There are areas of colder than normal Bering Sea surfaces. Also the coastal margins of the Gulf of Alaska see average to sometimes even colder temperatures. And we have a significantly warmer temperatures in the western North Pacific. We can describe those patterns of temperature anomalies are not random. We can describe them with a mathematical index, and we call it the Pacific Decadal Oscillation Index. We'll use this. Or Pacific Decadal Oscillation. It switches from positive to negative. Positive if we have warmer than usual temperatures in the eastern North Pacific. Negative if it's the opposite. And what's very evident, those indices, they can last up to decades. Therefore, decadal oscillation, they can last for a long time. And also what we see more recently, in 2024, we had a new record negative PDO, Pacific Decadal Oscillation, almost at -4 in summer and fall. And that record was even, we even got a new record last July when this index dropped the first time on record here. This record is from 1950, below -4. So there was something striking, and we thought, oh, what's going on, and how is it related to our temperatures? Those are climate division temperatures. Of course, if the sea surface temperatures are colder than normal, you would expect colder than normal temperatures in the adjacent areas. But we can see also somehow suppressed temperatures all across Alaska if the Gulf of Alaska and the Bering Sea have different temperature curves. So there's a connection, and we wanted to further, so negative PDO, moderate temperatures across Alaska. We wanted now to further look a little bit, what does a positive and negative PDO mean? How is the circulation, atmospheric circulation different? And what are main features? Thinking about the allusion low, extreme weather events, or even wildfire. Do wildfire occurrences change if the PDO switches from negative to positive? Or what are the connections? And that's where AI comes in. We did a traditional or classical AI technique called self-organizing map technique. You basically look at weather situations. You have a catalog of weather situations. Each weather situations, we call it node. It's basically a pressure distribution, or in this case, the height of a pressure level. And you select certain nodes and see and compare those nodes to all the daily pressure distributions of a certain period. We used as a period 1950 to 2024 and looked at the differences between positive and negative. And we also, the way it works, you have a hypothesis. You, of course, thought if the waters are colder than normal, you probably have some upwelling occurring, and you have some winds which go from land to the sea, so that the water is pushed away and lower waters can come up. And it was a little bit different. You have, what we found is you have more equator-ward winds, that's true. And especially in the Gulf of Alaska, those winds tend to move the water a little bit offshore and cause lower water to come up and cool down the ocean. The allusion low was slightly shifted, and of course, knowing this technique helped us to prove our hypothesis, and it's always a lot of fun if you work for for a week and you want to understand connections, and then it works out. It was really fun, and then of course we had extreme events happening, like last October when we had ex-typhoon Halong. You probably remember all the catastrophic impact. That's a satellite image of Halong developing in the Philippine Sea, moving up to Japan, where it got stronger and became a Category 4 typhoon, Category 4 wind speeds above 130 miles per hour sustained. And there was also precipitation measured within 3 hours, 7 inches of precipitation near Japan. So a lot of energy. And the path of this extreme Halong was first to the north and then to the east and straight across the Bering to Alaska. The energetics of the typhoon, of course, you need a lot of heat, and that heat was provided by those above normal temperatures in the western Pacific, which we have typical during the negative BDO phases. So there's a clear connection. The energy fits, and it was possible for this storm to develop. During the path, it crossed, of course, the Bering. It got into colder water. It became an ex-typhoon. The wind speed decreased, but still it hit Alaska. Wind speeds were measured up to 100 miles per hour. We saw those pictures from Kipnuk, where 90% of the buildings were destroyed. One person was unfortunately killed, and many people had to leave, and they were displaced and are still suffering from all the consequences. That was a very extreme, tough event last October. And then we have wildfires. Who knows this area? That's Gold King Airstrip down there. My colleague Bill, he's still sweating because I dropped him off there a day before this picture. And fortunately, I picked him up again. So there was quite a fire there. That's the time series. Those bars show the acreage burned from Alaska wildfires. And what's very striking, of course, who remembers 2004, our most extreme fire year? It was over 6.5 million acres burned, extreme fire year. Then we had 2005 extreme, and 2015, a lot of extreme fire years. And so in general, we have an uptick, an increase of fire acreage. That was on the left top. That's last year. We had 1 million acre burned, and fortunately, with more humid weather in August, the fires were extinct pretty quickly. But what's very striking, we also have to look at our neighbors. We got a lot of smoke last year also from Canada. Canada experienced in 2023 this devastating fire year, 37 million acres burned. If you compare 6.5 million in Alaska, 2004, 37 million in Canada, and then last year, 22 million acres. So they had a very stable first drought and very stable weather situation, and the fires just burned and burned, and it was quite devastating. And I'm very concerned once the BDO changes and once we have everything fits together, low snow cover, early fire start, we might face another devastating fire year in the future. With the fires, we look in our group quite a bit at fire emissions, and And from the Canadian fires, there were in 2023 an amount of 2.7 gigatons estimated, gigatons CO2 emitted in the atmosphere. That CO2 contributed, the smoke in general spread hemispheric around the whole globe. And 2.7 gigatons, 1 gigaton is a cube of water with a length of 1 kilometer. So it's quite an amount. For comparison, it's half of the annual fossil fuel emissions from the US that was produced. But if we look at this, those measurements of CO2 across the globe, we can see CO2 rises quite constantly. So it's distributed around the globe, and every regional source counts. And yeah. Some of our work, who knows those smoke forecasts? So we produce them in our group. That's work. Rich mentioned the WRF model. So we collaborated with experts in the field and implemented the parameterization of wildfire emissions and plume-rise model into WRF. And we provide those forecasts daily. Actually, the computer which runs those forecasts stands in Roosby's office. And now, from wildfires, it was actually wildfires, because those forecasts, when they are wrong, then we typically miss a fire. And in Alaska, we still have lots of fires which are even not detected. We have fancy satellites, but often cloud cover, and then the satellites don't see through the clouds. We use more and more techniques like microwaves and radars, which can see through clouds, but still we miss wildfires. And so we came across hyperspectral remote sensing, which is a relatively new technique for environmental sciences to look into wildfires and other environmental change. Our HiLab was founded in 2013. It was the brainchild of our former provost, Anupma Prakash. And she got funding from the National Science Foundation to buy the equipment. And nowadays, we use those cameras and instruments heavily in airborne configurations and on my plane. And we do ground measurements. We have calibration facilities. And I give the mic now to my colleague Roosby to introduce more about hyperspectral remote sensing, what it is, and what we are doing. Thanks.
Okay, thank you, Martin. In this part of the talk, I will talk about hyperspectral image processing. What is it, and what's the motivation behind using these sensors, where AI comes in to solve hyperspectral tasks, and which projects we are working on, and on those projects that are using hyperspectral imaging. To start, let's look at this short animation about hyperspectral imaging. Hyperspectral imaging is a passive remote sensing technology. By passive, it means that it just captures the light from the surrounding, that is sunlight. It's not active like radars. And it's optical remote sensing, so it captures the light from the ground surface. To do this, we need a hyperspectral instrument based on the physics of refraction. It works. But what is the difference between ordinary photos and hyperspectral images? In ordinary photos, like what we take using our cell phones, We just use 3 different bands, R, G, and B, with wide bandwidths. But in hyperspectral imaging, we use hundreds of those spectral bands with very narrow wavelengths. And there are different configurations to put hyperspectral sensors. It can be spaceborne with satellites. It can be airborne by airplanes, or it can be used also in field and also laboratory setups. So here you can see 4 different setups. Ground truthing, it means we go to field and we capture data using either RGB images or field spectrometers. We can use Martin's plane in airborne configuration to capture hyperspectral data using sensors. And AVIRIS also is an airborne hyperspectral sensor operated by NASA. And Landsat is multispectral. A satellite is a multispectral sensor on board of a satellite. Oops. So each material on the ground surface has its unique way of reflecting light. So for each of those materials, we have a specific spectral signatures. One of the advantages of airborne hyperspectral systems is higher spatial resolution, as you saw in this animation. So even for different kind of vegetation, different kind of trees, we have different spectral signature that we can use those signatures to distinguish between those classes. And using those spectral signatures, we can classify land cover into all different classes. For example, in this application, we want to do vegetation and tree classification. And here, AI and machine learning can help us to do the classification part. So this study about the boreal forest is very important for Alaskan communities, for the safety of the community, as Martin mentioned, because of the wildfire in Alaska, we need to study vegetation types and wildfire fuel classification. So with this large number of spectral bands, hyperspectral data introduces a new dimension to optical remote sensing, a spectral dimension. As you see in this slide, after doing hyperspectral survey, we acquire a data cube, a 3D data cube like this one here. And for each pixel, we have a spectral signature of that pixel that can be related to the specific material inside that pixel. For example, here you can see how a spectral signature changes while we are scanning ground surface using Hyperion, legacy Hyperion satellite sensor. That was the first hyperspectral sensor operated by NASA on EO1 satellite. There are 3 different classes here. water, vegetation, and fallow. And you can see when it moves to water, it's more similar to water spectral reference, and for vegetation and fallow, the same. At HiLab, we are equipped with two different hyperspectral cameras. First one captures visible near infrared wavelengths, and the second one captures shortwave infrared. Both of them are used in airborne configuration on an airplane along with IMU GPU unit operated by Martin, and it captures 457 different spectral bands. Before processing hyperspectral data for specific applications, we should pre-process data. There are two main pre-processing steps. The first one is geo-rectification or georeferencing that aligns pixels on the raw hyperspectral data to the real-world geographic coordinates. And the second step is atmospheric correction that corrects Earth's atmospheric effects and also converts the top of atmosphere radiance to bottom of atmosphere reflectance. But after these steps, the data is ready to be analyzed for a specific application, but we have a large amount of data that needs smart computer algorithms to deal with. Here, AI comes in and helps us to do hyperspectral tasks. Most of us know AI with ChatGPT and generative AIs, but there are differences between ChatGPT and AI algorithms that we use for hyperspectral analysis. ChatGPT usually works with inputs like text, but AI for hyperspectral analysis uses physics in spectra in this case to analyze the data. There are different categories of AI, classical AI that does not learn from data, machine learning, and deep learning that learns from data. But there are differences between machine learning and deep learning. Machine learning usually needs handcrafted features, but deep learning learns automatically these features from the data. To better understand the difference between machine learning and deep learning, we look into one famous application, face recognition. As you can see here, to use machine learning for face recognition, we need manually extracted features using image processing techniques, and then a machine learning algorithm like shallow neural network to be trained and identify faces by matching them to the database. But in another approach, deep learning, we use lots of samples to learn the deep network, like convolutional neural network, and then after training, it can recognize faces. Deep learning is well comparable to how kids learn new objects. To learn new objects to kids, we usually don't describe the object, but we show them many, many examples to learn. Another difference between machine learning and deep learning is about the size and complexity of the network. Artificial neural networks originally comes from the comparison or inspired from the biological neurons. So building blocks of artificial neural networks are simplified models of biological neuron. In this toy example here, we want to classify 2D feature space into two different classes, blue and orange. So we have a whole data set, but we don't use all of these samples to train the network. We just use 20% of the data. If we use a very simple network with 2 layers, and for each layer we use 2 neurons, probably it fails to solve the problem. As you can see here, it just can do a linear classification and fails for the data set, for this data set. But if we add more layers and more neurons to each layer, it can solve the problem very accurately. Size and complexity of deep learning models is not the only parameters. There are many parameters that should be taken care of, but this is beyond of this talk. If you are interested, you can go to Playground from Google TensorFlow to explore more examples. But how this deep learning technique can be applied to hyperspectral tasks? Again, we used classification as an example. To classify hyperspectral data cube, we can use both pixel level or image patch level classification. For pixel level classification, we use the spectra from each pixel. That is a one-dimensional signal, so we need one-dimensional convolutional neural network to be trained and classify that pixel into one of the output classes. For example, in mineral application, it could be different minerals like hematite, magnetite, and so on. And the final output is the classification map, in this example, mineral map. Another approach is image patch level classification. In this case, we use data from neighbors as well as the data of that center pixel. So we have the neighborhood information that can help us to do the classification more accurately. So the input to the deep network in this case is a 3D image patch. So we need 3D convolutional neural network to solve the problem. And again, the output is different classes and classification map. So let's talk about the hyperspectral imaging applications in real world. There are a variety of applications for hyperspectral imaging, from ecological applications like glacier and snow analysis, ocean colors, wildfire investigations, permafrost research, harmful algal blooms, mineral identifications, and even searching for new sources of energy. In healthcare, it can be used, for example, in robotic surgery, where we want to distinguish between malignant and benign tissues in a real-time manner. And in industry, we can use it for quality control, for example, to assess the quality of salmon fish in food industry. Despite harsh weather conditions in Alaska, because we are based here in Fairbanks in interior Alaska, and owing to Martin's knowledge of atmospheric sciences, we usually find the best weather windows to fly over areas of interest in Alaska. And this map shows several data sets that have been captured by HiLab. And you can see it ranges from the southeast near Juneau in areas like Lincoln and Mendenhall Glacier to Bering Sea, and also up to north in mining sites like Red Dog Mine and Ambler. And we have different data sets for different applications, from mineral to snow, glacier, coastal analysis, wildfire, and wetland mapping. In the remaining slides, I will talk about some of examples of these projects. The first application is ocean colors. What color is Alaska's ocean? Leah Hartel and HiLab team did a comprehensive study of turbidity mapping in Kachemak Bay. In this slide, you can see two different time stamps and hyperspectral data of Kachemak Bay You can see the patterns of glacier and clear water in this slide. If we compare the spectral information from hyperspectral data with those of multispectral satellite sensors like Landsat 8 and Sentinel-2, we can see much more information is provided by hyperspectral data that can be used to classify clear water and glacial water. Using hyperspectral data mixing methods, we can estimate glacial water abundances. So in this slide, you can see the result. It shows the glacial water abundance, and it's strongly affected by fresh and also silty water from the nearby retreating glacier. So this hyperspectral data can be used as a baseline for analysis of future multispectral or hyperspectral satellite time series. Another important application for Alaska and globally is harmful algal blooms or HABs. Harmful algal blooms are rapid growths of algae that can be very dangerous for animals, and also with food consumption, seafood consumption, it could cause illnesses in human as well. But what's the reason of these HABs? They are growing and increasing in both frequency and severity, often because of the climate change, warming waters, nutrient runoffs, and also changing ocean conditions. So climate change is warming Alaskan waters, maybe faster than any other regions in the world, and it creates conditions that allow HABs to expand into the areas that we didn't have HABs historically. USGS did a study and recorded spectral signatures of different bacteria in harmful algal blooms, as you can see in this plot, compared to the spectral signature of clean water, the solid light blue curve. So with the differences between the spectral signatures and using hyperspectral data, for example, this is hyperspectral data set acquired by HiLab at Kotzebue, Alaska. And also using machine learning algorithm, we can classify harmful algal blooms and non-toxic blooms and also clean water. HiLab is also publishing public data sets for environmental science. One of recent publications is HiLab Airborne SNOW-X dataset. It's part of NASA SNOW-X field campaign, and the imagery was collected on several snow-colored boreal forest environments in Alaska, including Farmers Loop Creamer Field and Caribou Creek. To have a better sense of the data size, size of this data set is about 160 gigabytes, comparable to watching 40 hours of a full HD movie. So again, AI can help us to reduce the size of this data set and extract meaningful information from that using dimensionality reduction and also representation learning models. Another interesting application is glacier analysis. This is part of Mendenhall Glacier dataset. Carl Schmidt and HiLab team studied the effect of light-absorbing particles and also snow grain size on spectral signatures of the snow pixels. Another important application for Alaska is wildfire monitoring. This photo shows wildfire near China Hot Springs. Chris Weil and HiLab team did a comprehensive study to map wildfire vegetation and wildfire fuel. As you can see here, there are differences between bare ground and different vegetation types. So using this information, we can classify wildfire fuel. So the output will be this classification map that can be used for wildfire management, and it can turn wildfire management from a reactive process to proactive process. While we are working hard to keep on environmental science studies, HiLab is also engaged in other applications, other classic application areas of hyperspectral processing, like mineral identification. Critical minerals is very important for Alaska and also US economy because it can be used in different high-tech industries, and it's also being used for electricals and many other applications. Here we use spectral signatures of hyperspectral data to classify different minerals. We usually use spectral reference libraries to compare and train machine learning methods to do the classification. HiLab did many mineral data sets. One of those is Coal Creek dataset. As you can see here, it contains 32 flight lines. And after all pre-processing and processing steps, we can produce mineral maps like the one you are seeing here that is overlain on digital elevation model. Closer look to these mineral maps based on two groups of mineral alterations shows the identification of different types of mineral in each group. One of the challenges in Alaska for mineral identification is vegetation. As you can see here, there are pixels that is a combination of vegetation and different types of minerals. So to address this challenge, in a recent study, we used deep learning to solve this problem. The problem is called spectral unmixing. To solve the spectral unmixing problem, we use deep autoencoder that consists of encoder and decoder, and using lots of samples that in hyperspectral data is pixels, and if depending on the size of the image, we have millions of those pixels to train the deep learning model. So after training, the outputs of encoder are abundance fractions for each mineral or vegetation, and the weights of decoder are decomposed spectral signatures. Another interesting application as a future insight is geologic hydrogen search using hyperspectral data. New sources of energy is always important. For Alaska, it's more important because for remote areas that we have in Alaska, we need this kind of energy, and also hydrogen fuel cells are more efficient and reliable in comparison to electric cells and batteries. So to search for geologic or natural hydrogen, we can use hyperspectral as an indirect indicator. There are two main pathways. One is identification of iron-rich minerals that are linked to geologic hydrogen, like olivine and serpentine, that I discussed in previous slides. And the second pathway is to identify and detect mysterious fairy circles that could be linked to geologic hydrogen. There are there are evidences globally that around these fairly circular structures, there are hydrogen sips, like in this case study in Australia, that these blue circles shows the level of hydrogen sips. If we measure spectral signatures for ground surface around those Faraday circles, there are differences in spectral signatures that using machine learning algorithms could be used to classify Faraday circles that are related to geologic hydrogen. To summarize, we use hyperspectral imaging for seeing the unseen. RGB images can just capture three spectral band, while hyperspectral data can capture hundreds of those. And the data from airborne studies can be used as a baseline for future satellite mission. And then AI can help us to turn these high volume of data in hyperspectral images to meaningful outputs like classifications, predictions, and different output maps. And the synergy between hyperspectral and AI can help us to, for decision making and policy making that can that can have real world impacts. Thank you very much for your attention, and we would be happy to take any questions.
All right, we have time for some questions. We'll start with the in-room audience. You can raise your hand, and myself or my friend and coworker Rod will bring you a microphone.
I can ask a question.
Okay.
Will you let me?
Yes.
Okay. For Martin, Rusbe, do you go out on the airplane with Martin?
Sometimes, but last time I got motion sickness, so.
Okay. Well, I was going to kind of ask about that, what a flight is like. How low to the ground do you go? Maybe walk us through that a little bit, kind of what happens up there. And does it get turbulent? Does it make anybody airsick? Because I'm thinking of going on the plane with you, remember?
I know, yeah. Actually, I told Rusby, I gave him some photos of some pretty pale faces, but he was just too shy to put them in. So as Rusby said, we are measuring the reflected sunlight. So I try to avoid clouds. I try to find situations where we have calm or no to little winds. We did for several years Link Canal, and to do Link Canal I needed clear skies. I needed low tides, no winds. You can imagine that's not Juno. And looking in the climatology, there are typically 2 to 3 days each summer which qualify. And we were actually able, I have to take the credit, I was able to hit those days for 3 years in a row. That only works to be, I flew alone. I flew long days, and I took off at sometimes at 3 in the morning in Fairbanks. Started at late morning in Juneau, and I had flying days. The maximum flying day was 16 hours a day, I remember. And you don't have the ability to stop for a restroom. So I don't drink much during the flights.
You're not making this attractive for me to go with you.
Once you fly a line, you do quick turns, steep turns, and try to get established on it's like a racetrack. And Juneau I'm especially keen of Juneau. I did overhead Juneau, and over the right in the flight path to Juneau Airport, Alaska Airlines was coming all the time, and they were just great. They knew I was not very flexible with flight heights, and they accommodated my mission very well, because I told them, you know, I only have a few hours, otherwise I have to come next year again. And so they were very helpful. And it helps to be right in Fairbanks. I can reach almost all our destinations the same day. I look at the weather, and sometimes I decide just a few hours before to go. And yeah, unfortunately, when Roosevelt joined me, his face was one of the pale faces. It was a kind of a torture. And I myself, when I drive with my wife in the car or with anybody, I'm not a good co-driver, but if I drive, I never get sick, but you know how it is.
Question right here, Sarah.
If you could show the public one map that explains what's happening in Alaska, which one would you pick? What spectral signatures or data layers make it so powerful?
You know, it makes hyperspectral imaging is a main key. I'm most concerned with the risks of wildfires and also those harmful algae blooms. Those are real challenges for Alaska. We don't have good fuel maps. They are actually quite bad in quality, outdated. And so I would use hyperspectral imaging for wildfire fuels more extensively, and especially also for harmful algae blooms, watch at ocean waters, because that can ruin our fishing industry quite a bit.
I can ask some questions from online. From Lisa on Zoom, what has been the environmental impact of these HABs on aquatic life?
Those HABs are known that they kill fish, that they are extremely poisonous, they could kill people. They can, there were some studies of HABs which were really extensive in the Bering Sea. And with slight changes in water quality, in water temperatures, they can develop. And yeah, they can really be fatal.
Question from colleague Chris Mayo on Zoom. With Murbach in 2022 and Halong in 2025, is this an indication of increasing typhoons entering the Bering Sea, or is this what would be expected based on the historical record?
You know, Murbach was the strongest storm after 70 years, that's the estimate. And it had even more energy than Halong had. Water levels rose locally by 12 feet. And we have, with climate warming, we expect more extreme events like Murbach and Halong. And they might enter the Bering Sea, or most likely in a higher frequency, hopefully not every 3 years. Like Murbach was 22, Halong 25. So hopefully we have a longer break, but more extreme events will come and enter the X-typhoons will enter the Bering Sea, yes.
Sarah, we have a question over here. Now a good time? Okay.
Kind of an odd question, given the breadth of what you've talked about. There's a tremendous amount of information, a lot of nuanced deals in different topics. What I was wondering was whether because you've touched on AI, I'm not very aware of that, and it's fairly early. I was wondering if you've stepped into and working with some AI out of desperation to try to pull more information out of these very complex data sets where you've got lots of information, and therefore you're trying to get some success by using AI to aid you in meshing things. So it's really above the breadth of the various topics that you've brought up here, and the two of you, we just heard about a dozen different nuances and information. Anyway,
I'm sorry for the widespread of the talk and you.
You'd be sorry. It's I wonder if AI can help you find it and then make it intellectually believable.
Yeah. It's maybe you want to respond.
Yeah, of course, AI can help us to extract more meaningful information from all the data set we have. But it's challenging. We need more ground truth data to learn AI. So it's one of the disadvantages of AI. If we don't provide them with good information, they cannot provide us with good results.
Like this self-organizing map example I showed before. In former days, you had a classroom full of students and gave them some maps and they classify it. And of course, now with AI, we can do it way faster or 1,000 times quicker, just on sitting on our computer alone. It's a nice tool, but often it normally doesn't help to understand the physics. It helps to do the statistics. And you have to be careful because you can also get a lot of wrong and stupid things. And that's the big danger. Anybody who uses ChatGPT, you can find very quickly just the opposite what's true. And this can't be true. And so you have to be very, very careful with AI. But applied correctly can save a lot of time. It can be powerful.
I think Rod's going to take one more question.
Well, I'm not.
Yes.
Well, I'm not,
pass
I'm
the
not
mic
asking
on,
the
please.
question.
Okay.
Okay, all right.
Thanks. Thank you. Somewhat along the same lines with the AI, there's been a lot of technological progress recently. I'm actually interested in the instrumentation itself. How has that advanced recently? You mentioned the resolution has really improved, in which you can get spectral imagery from the ground. Can you explain that a little bit, how the technology has advanced to allow you to get better data? And how that also applies to the instruments that you're using with your airplane and versus satellite?
Yeah, I mean, there are millions and millions of dollars going into also the hardware development. Hyperspectral imaging got a lot of support through medical sciences. I think you touched base on it, especially skin cancer analysis and those. There was a lot of development done. The technique itself, it was refined. It's more precise nowadays, but a lot of effort goes in to make those cameras more compact because of the drone industry. Everybody wants to do airborne hyperspectral work with drones. And we get those requests all the time. For us, the problem with drones is you still need to get to the site. So you need a helicopter and then fly somewhere in the wilderness and launch the drone, and which is more complicated than just flying with the airplane. But the technology, it is getting better and better. We use a Norwegian company called Hyperspecs. They have now big contracts with the European Space Agency to develop new instruments for satellites. And you can imagine weight, precision, and also robustness of the instruments is a key. And so, yeah.
Yeah, I can add that always there is a trade-off between a spectral resolution and a spatial resolution, so we cannot improve both of them together. because it's limited by signal-to-noise ratio of each pixel on the image or on the sensor. So if we want a better resolution in a spectral dimension, we should lose some spatial information, and vice versa.
All right, I think that's all the time we have for questions. Thank you again to our speakers.
Thank you.